Okay, in this next video we're going to look at peptide synthesis, not in a biological setting, but rather in a synthetic setting, meaning in a lab. And the goal with peptide synthesis is you want to take one amino acid, I'll call that AA number 1, and we want to link this together with a second amino acid. It could be the same, it could be different, but we'll call this amino acid number 2. And during this process, what we're going to be doing is we're going to form a new amide bond. But specifically, it's an amide bond between two amino acids. So we refer to this as a new peptide bond. It's just a fancy word for a bond, an amide bond specifically, that occurs between two amino acids. Now, on the face of it, it looks pretty straightforward, right? We just want to link these two molecules together. Looks like normal acyl substitution. But in reality, it's a lot more complicated than meets the eye. So what I want to do today is kind of go through some of the initial problems with linking these amino acids together, and then we'll take a look at the solutions for working around those problems. So let's take a look at problem number 1. And what I'm going to do is I'm going to kind of abbreviate these amino acids just to save some time. So amino acid number 1, I'm just going to show the carboxylic acid end. So I'll just say AA number 1, and we're just going to abbreviate the R group and only show that carboxylic acid. And then over here, I'll do amino acid number 2. And in this case, all I'm really concerned about is the amine side of that amino acid. I'm not really concerned with anything else, right? Because what we want to do is form some sort of new bond between these two groups, right? All right, here's the issue though. When we look at this, if we try to put these together, instead what will happen is a proton transfer. That is to say, we'll have acid-basic chemistry occur, right? Because over here, this acts as an acid, and then this acts as a base. So that's a pretty big problem, right? If we want to do this chemistry, we want to actually do nucleophilic acyl substitution, not just a proton transfer, which would shut the entire reaction down. All right? The second problem is when we look at this, this is a really bad leaving group. So we must turn this OH group into a good leaving group. All right, and I know some of you might be thinking, well, we did this with esters, right? We were able to convert a carboxylic acid to an ester by treating it with strong acid, and we did the Fischer esterification. We can't do that here, because if we treated it with strong acid, we would also protonate this amine. And if we protonate the amine, it's not going to be a good nucleophile anymore. So we have to get a bit more clever. And if you think about how we made amides in our carboxylic acid chapter, we had a few options. One was to convert to a acid halide, meaning a chlorine, using thionyl chloride, that's SOCl2. It's not really as common to do this when you're making peptides because SOCl2 will also react with other functional groups. So normally what people do is they use these reagents called peptide coupling reagents. And the main goal with the peptide coupling reagent is to turn that OH group into a good leaving group. That not only turns it into a good leaving group, but it prevents that acid-base chemistry from occurring too. There's a huge number of peptide coupling reagents, but I want to show you just one that's in our textbook. So let's do this. We'll do solution, use a peptide coupling reagent. And almost universally, this is what chemists do now. Instead of using thionyl chloride, it's just a lot easier. It's significantly less sensitive to moisture and things like that. So in this reaction, what we do is we take our carboxylic acid for amino acid number 1. So I'll just go ahead and say that this is amino acid number 1. And what we want to do is we want to react this with our peptide coupling reagent. And the one that they show in our textbook looks like this. It's got a carbon-nitrogen double bond, and then off of that nitrogen, we have a cyclohexyl group, right? meaning a cyclohexane is coming off. Clean this up a little bit. And this gets abbreviated a little bit. This whole group, that cyclohexane derivative, is just abbreviated as just CY. Same thing down here. So it's got two cyclohexyl groups. So the name of this is called dicyclohexyl. And then that middle group is called a carbodiimide. Now this is kind of a mouthful. So what people normally refer to this is DCC. So we can go ahead and just abbreviate this as DCC, our peptide coupling reagent. All right, the first step of this reaction is going to be acid-base chemistry. Like I said, this carboxylic acid is acidic, so it could react with any sort of relatively weak base. And in this case, our peptide coupling reagent has these nitrogen lone pairs coming off that can act as a weak base and steal this proton. So we'll go ahead and we'll make our carboxylate salt, meaning our deprotonated carboxylic acid. All right, we're not quite done yet though, because now we've got a nitrogen with a positive charge on at least one side of our DCC reagent. So let's go ahead and draw this out and we'll show this nitrogen with a positive charge. Because that nitrogen has a positive charge, it's not super happy, right? It wants its electrons back. So in the next step, what we're going to do is we're going to have our oxygen on our carboxylate attack this carbon and then kick electrons right back up to that nitrogen. Let's take a look at what this intermediate looks like. So now we've got our oxygen bonded to a carbon. The nitrogen now has a single bond to it with a hydrogen. We still have this cyclohexane coming off that nitrogen. And then underneath, we still have a double bond to this nitrogen. And we've got this group still bonded, to cyclohexane as well. All right, so we've got this neutral intermediate now, but we're not done. What we're going to do next is we're going to treat this with our second amino acid. And what I mean by that is we want to focus in on this amino acid number 2. So I'm going to show this in green just to keep things consistent. So let's go ahead and show amino acid number 2. And again, I'm only going to be focused on the amine end. So we'll just say amino acid number 2. Okay. So what can happen next is the second amino acid can actually attack into the carbonyl and kick electrons up to the oxygen. So let's go ahead and show this next intermediate. And as you can tell, it's getting a little bit big and complicated, but we'll try to go slowly and show how this works. So what we have now is a nitrogen that's added in. We still have the rest of our organic groups kind of hanging off. And we'll go ahead and fill them all in. All right, so we've got this intermediate now, and we're not quite done yet, right? As we've seen before, we want to get rid of one of these protons on this nitrogen. It's not happy with the positive charge. So let's do a proton transfer and move it to the next best position. So I'm just going to write plus minus H plus, and we're going to get rid of that and move it somewhere else. Specifically, what we're going to do is we're going to give it to this nitrogen down here. Okay. So now this oxygen still has a negative charge, but this nitrogen over here is going to be neutral. And we can go ahead and show the rest of our organic material. And let's actually show this as a bond right here. So what we're doing is we're moving that proton from this nitrogen over to the other nitrogen, right? So it's just a simple proton transfer process. A lot of these are done in protic solvents. However, in this case, it will work even just by doing proton transfers using the amino acids themselves. Okay, so now we're almost ready to go. It doesn't seem super intuitive, but this is a great leaving group. Okay, so let's see how we can kick this off. So in this next step, we're going to take this negative charge, clamp down. This is going to get kicked off and form a new double bond, and then we're going to kick electrons all the way over to that nitrogen. Okay, so now we've gone ahead, formed our new double bond, but we have our new bond to our nitrogen, and we've got our R group here. So in this process, what we've done is we've created this new peptide bond. All right, and then the leaving group that we've generated looks a little bit weird, but what it is something called a urea. So let's go ahead and show what this looks like. A urea is basically something that has an amide coming off of both ends of a carbonyl compound. So this whole group right here is going to be our leaving group for this reaction. The nice thing with this is you can actually wash this away using simple extraction chemistry. So the cleanup really isn't that bad, but this is called a urea leaving group. And like I said, there's a variety of peptide coupling reagents, but a lot of them actually do produce urea type leaving groups on them. All right, so a pretty good mechanism. It avoids all that unwanted acid-base chemistry. However, the atom economy is fairly low, so that is one pitfall. I did want to talk about another problem though, but let's take a pause right now before we get into that second problem.